Back when we talked about series and parallel circuits in the first place, we talked about how series circuits use less power than parallel circuits. Having spent a little bit of time defining power and energy a little bit more carefully, I'd like to go back now and do a video where I explicitly show that series circuits have less power than parallel circuits. So here I have a series circuit that's powering 3 10 ohm light bulbs, and here I have a parallel circuit that's supplying the same 3 10 ohm light bulbs. Now let's start on the left here, and we'll solve this circuit. We're going to start here. We're going to go around the loop. I'm going to go a little quickly in this video because I've already done a video where I solved series and parallel circuits, so if you want to see that, go back and look at those videos specifically. Going around this voltage loop, I'm going to go up a 9-volt battery, and then down V1, V2, and V3, the voltage of the 3 light bulbs, respectively. Now, I don't have any common variable here, so I'm going to recognize that the current everywhere in the circuit is constant. And then it will be useful to replace all of those voltage expressions with equivalent expressions involving current, since it's the same current at all places in the circuit. So 9 volts, V1 then would be equal to 10 times the current. V2 would also be equal to 10 times the current, the resistance at resistor 2 times its current, plus V3, also 10 times the current. So 9 volts, and collecting my like terms, 10 currents plus 10 currents plus 10 currents is equal to 30 currents. I get, isolating for current, I think this is going to be 0.3, but just make sure here, yep, 0.3 amps of current. So if I want to consider the power coming out of this bulb, I can consider it to be the current times the voltage, which would be 0.3 amps times my 9 volts, which would give me a total power of 2.7 watts. Now let's do that same calculation, but for our parallel circuit. So here I'm going to do 3 separate loops, and what I'm going to realize is that, and this is common to parallel circuits, since each of these loops only goes up the battery and down the resistor, then if I go up 9 volts, I have to come back down 9 volts at each resistor respectively. What that means then is I can find the current at each resistor. So let's go this 1, 2, 3, although it's the same for all of them. V equals IR, and in all cases here I have 9 volts and a 10 ohm resistor, and so I'm getting a current of 0.9 amperes. I could do that for 1 or 2 or 3. Since I've made all these resistances the same, the calculation works out the same. So then I can recognize that the current from the battery has to supply all 3 of those currents, I1, I2, and I3. So IB is going to be equal to I1 plus I2 plus I3. Since each of them is 0.9 amps, I can get a total current of 2.7 amperes. Again, looking at the power coming out of the battery then, using its current and its voltage, it's supplying 2.7 amperes at 9 volts. To get a total power of 24.3 watts. Obviously, quite a difference here. The power associated with the parallel circuit is much greater. Now we could classify that as a pro or a con depending on the situation. So for example here, this 2.7 watts could be a pro if we're dealing with a battery-driven device that needs to operate on a small amount of power. Alternatively, if we want these light bulbs to be nice and bright and we're coming from a source that isn't limited like a battery, we might want the high power. Either way, depending on our situation, we can imagine which of these two types of series that we choose to accomplish our goals.